Hi, this is Chris, and we are taking a look at an introduction to torque. So, in this video, we're going to talk about its basic formula and basic principles, and we're going to do two calculations. So, let's go ahead and take a look at the formula. So, for torque, we have this formula here that your torque is equal to Rf sine theta, and we'll talk about what those variables mean in just a sec. But first, let's think about what torque means conceptually. When you talk about torque, you're really talking about rotation. And when an object rotates around a fixed point or a pivot point, as you'll hear it called both ways, that would be an example like what we see down here. So maybe this rectangle that we see, maybe this represents like a door handle, and maybe you've got some sort of fixed point here at the end of your door handle. And so if you picture grabbing this door handle and you go to push down on the handle, so the handle rotates and this point stays fixed. So it would rotate around a fixed point. So when we're looking at R is going to be our distance between the applied force and the fixed point. And you can think of it like a radius. Most of us associate with R with radius, and that's okay, because if you look, we are rotating this object. So if I were to zoom out, right, in this scenario, you could kind of picture how this handle, in theory, could rotate all the way around and become, like a full circle. So R would be, if your fixed point is the center of that circle, R would be your radius. But most of the scenarios that we see with torque, we're not going to see that full circle. We're going to look, just a little bit closer in. And so sometimes it's easy to lose the appreciation of that concept of a full circle. But that's what torque is. You have rotation around a fixed point. And so R will represent your distance. F represents your force. That one we probably know by this point in physics, hopefully. And then your theta value. So sometimes there's going to be an angle, and theta is going to be the angle between your applied force and what we call our axis of rotation. So here, if this is our axis down the center of our door handle in this example, then that means if you're applying a force, it's not always pushed perfectly straight down. Sometimes it is, right? But the angle that we're looking at sometimes might be based on, maybe I'm trying to open the handle, but, I'm carrying something and I can only kind of reach a pinky out and I sort of grab onto it at an angle and I sort of pull this way. Well, then that's okay. That would be my theta value there. That would be my angle. And if you think about where that comes from, it comes from the fact that this could be a triangle, and what's going to apply your force downward on the handle is going to be the vertical component. So if you think of SOHCAHTOA, opposite over hypotenuse, for sine, your sine theta would be opposite over hypotenuse. Your hypotenuse here is really your force. So if you think of this as your force, and you're trying to find this vertical component, so this would be your force just in that y-axis, you would have force times sine theta, or F sine theta, this part of our equation, is really just representing our vertical component of force pushing straight down on that handle. And that's why numerically here, when you're talking about torque, you're looking at a scenario where you have an angle of 90 for sine. Sine 90, remember, has a maximum value of 1. I'll put that over here in the corner just as a good reminder. And then your minimum value for sine in that first quadrant, sine of 0, would be 0, which basically means if you're thinking about applying a force, if I apply a force straight down on this handle, that'll be the easiest way for me to allow that handle to rotate. Whereas if I applied a force in this direction on the handle, you can push all day long, but if you're applying a direction perfectly parallel to that axis of rotation, that handle's not going anywhere, because you're taking your value of torque, you're doing Rf times sine of 0, which would be 0, which means you're applying 0 torque to the handle in that scenario. So now let's take a look at a situation where we might be given some values. So to do a couple simple calculations, let's say you apply a force of 10 newtons and at a distance of 2 meters from your fixed point. And in this case, directionally, we're going to say that we have a theta value of 90. So that means you're applying your force. This is going in this scenario. Let's say we apply it straight down. So we'll still use this same example with our door handle. We're applying a force straight down. So if you're asked torque, then to solve for that, we're simply plugging into the equation that we had above. And let's see if we remember that equation. So hopefully we learned something so far. Torque is RF sine theta. So mini pop quiz there. Hopefully we remembered that. If not, by the end of this video series on torque questions, you will definitely know it. And here, to solve for our torque, we plug in our value for R, which is our distance between the applied force and the fixed point. We plug in our value of F, and we plug in our angle. And when we multiply those out, 2 times 10 is 20, sine of 90 is 1, 20 times 1 gives us 20. So that would be our value for torque in this scenario. And now let's do one more calculation here. So we're going to leave our equation up, and we're going to change out some of these values just to see how that impacts our value for torque. So let's change up our angle. Let's say in this case that we're applying torque at a 30-degree angle. Or we're applying a force rather at a 30-degree angle and trying to generate torque. So again, same scenario. However, we're going to have 2 for our radius, 10 for our applied force, but now we have a sine of 30. So here 2 times 10 is 20, but then sine 30, and for most complex questions with angles that are not part of your unit circle, you'll probably be allowed to use calculator if you need an exact decimal value, but in this case, sine 30, that's one we should probably know. Sine 30 is 1/2. And 20 times 1/2 gives us 10. Which means that just by adjusting the angle, then we're going to be applying, in this case, only a fraction of the original torque, which is rotationally here. You're applying a torque of 10 rather than a torque of 20, which kind of makes sense, because back to our door handle example, remember, if we are looking at this angle in here, if you apply a force at an angle, right? Remember, you're carrying a bunch of stuff, you barely grab onto that door with maybe just one little pinky, you're trying to pull that handle down. It's a lot tougher to get that handle to rotate when you're pulling at an awkward angle like that, because the vertical component of force that you're applying is much smaller. So whenever we talk about torque, just remember, torque is rotation. Our equation for it is RF sine theta. And coming up next, we're going to take a look at a situation where we have a fixed point not at the end of a particular axis of rotation like this, but we're going to look at what if we have a fixed point somewhere in the middle. So this is going to be an example more similar to what you would see on a seesaw or a balance. So stay tuned and we'll dive into that next.